This is chapter 12, cryptography. My name is Brent. Cryptography is the process of converting plain text, which is readable text, into ciphertext, which is unreadable or encrypted text. Cryptography can be used on data that people or organizations want to keep private or data that should be accessible to only certain users. In other words, cryptography is used to hide information from unauthorized users. Decryption is the process of converting ciphertext back into plain text, also called clear text. Cryptography has been around for thousands of years. For example, some Egyptian hieroglyphics on ancient monuments were encrypted. Parts of the book of Jeremiah were written using a cipher or key known as atbash. This is called substitution cipher, which reversed the alphabet, like A was Z, and only the person that knew this mapping could decipher the message. Julius Caesar developed a similar substitution cipher for encrypting messages by shifting each letter of the alphabet 3 positions. The study of breaking encryption algorithms is called cryptanalysis. Hackers find the challenge of breaking an encryption algorithm intriguing and continue to force developers of encryption algorithms to push the envelope in finding harder to break algorithms. When a new encryption algorithm is developed, cryptanalysis is used to ensure that breaking the code is impossible or would take much more time and many resources that the attempt to be impractical. The most famous encryption device was the Enigma machine developed by Arthur Scherbius and used by the Germans during World War II. The operator typed a letter to be encrypted, and the machine displayed the substitution character for that letter. The operator then wrote down the substitution character and turned a rotor switch. He or she then entered the next letter and again wrote down the substitution character Enigma displayed. The code was first broken by a group of Polish cryptographers and then by the British and Americans. The machine the British and American cryptologists used for breaking the code was called the Bombi. The main purpose of cryptography is to hide information from others, and there are many methods of hiding that data that don't use encryption. One is steganography, a way of hiding in plain view in pictures, graphics, or text. In 1623, Sir Francis Bacon used this form by hiding bits of information in variations of the typeface used in books. Modern cryptography uses encryption algorithms to encrypt data, banking transactions, and online web transactions, wireless communications, and so on. An encryption algorithm is a mathematical function or program that works with a key. The algorithm strength and the key secrecy determines how secure the encrypted data is. A key is a sequence of random bits generated from a range of allowable values called a key space, which is contained in the algorithm. The larger the key space, the more keys can be created. For example, an algorithm with a 256-bit key space has a 2 to 256 power possible keys. The more random keys that can be created, the more difficult it is for hackers to guess which key was used to encrypt the data. So only using an 8 random keys as shown here makes the algorithm too easy to crack down. Here are the types of algorithms. Symmetric uses a single key to encrypt and decrypt data. Both the sender and receiver must agree on the key before data is transmitted. Symmetric algorithms support confidentiality, but not authentication and non-repudiation. However, they're at least 1,000 times faster than asymmetric algorithms. Asymmetric uses 2 keys, one to encrypt and one to decrypt. Asymmetric algorithms support authentication and non-repudiation, but are slower than symmetric algorithms. Asymmetric algorithms are known as public key cryptography. Hashing is used for verification. Hashing takes a variable length input and converts it to a fixed length output string called a hash value or message digest. Crypto systems using symmetric algorithms have one key that encrypts data and one key that decrypts data. If a user wants to send a message to a colleague, he or she encrypts the message with a secret key. Then the colleague must have a copy of the key to decrypt the message. If the user wants to encrypt a different message and send it to a colleague, a different key must be used. If there's hundreds of colleagues, there must be hundreds of keys, and it's hard to keep track of which key to use. Another problem is how to send the key. Emailing it can be dangerous because the message can be intercepted. Two types of symmetric algorithms are used currently: stream ciphers and block ciphers. Stream ciphers operate on plain text 1 bit at a time. Messages are treated as stream of bits, and the stream of cipher performs mathematical functions on each bit, which makes a great candidate for hardware or chip-level encryption devices. Block ciphers operate on blocks of bits. These blocks are used as input to mathematical functions that perform substitution and transposition of the bits. When a block cipher separates input into blocks, it must add padding to fill the block. This padding leaves the cipher susceptible to attack. The National Institute of Standards and Technology, the NIST, wanted a means of protecting sensitive information called data encryption standard. So in the 1970s, it invited vendors to submit data encryption algorithms. The best algorithm would be the standard for encryption methods for the government agencies and private sector companies. IBM created a 120-bit algorithm called Lucifer, and NIST accepted that. However, they wanted to make some modification and reduce the key size from 128 to 64 and name it the data encryption algorithm. Time has taken its toll on DES, and they needed to come up with a new standard called triple DES, 3DES, to make it more difficult for attackers to crack the encryption code. 3DES performs the original DES computation 3 times. Again, time took its toll on 3DS, and they released Advanced Encryption Standard, AES. NIST put out a request to the public for a new encryption standard, asking for a symmetric block cipher capable of supporting 128, 192, and 256-bit keys. Out of the finalist, Rindle was chosen because of its improvements in security, efficiency, performance, and flexibility. International Data Encryption Algorithm, IDEA, is a block cipher that operates on a 64-bit blocks of plain text. It uses 128-bit key and is used in PGP encryption software. It is free for non-commercial use, but you must purchase a license for commercial use. Blowfish is another block cipher that operates in 64-bit blocks of plain text. However, the key length is variable from 32 bits up to 448 bits. It was developed as a public domain algorithm by Bruce Shiner. RC4 is the most widely used stream cipher. It's used in WEP wireless encryption. It's because of the way RC4 is implemented in WEP that finding the key with error cracking programs, for example, is so easy. RC4 is considered difficult to break, but should be avoided for most applications. RC5 is a block cipher that can operate on different block sizes, 32, 64, or 128 bits, and the key size can reach up to 2048 bits. Instead of the single key used in symmetric algorithms, asymmetric algorithms use 2 mathematical related keys so that data encrypted with one key can be decrypted with another key. A public key is openly available in many cases. Public keys can be downloaded from websites for the public to use. A private key is a secret key only known by the key owner and should be never shared. There are different ways to encrypt a message with asymmetric algorithms, depending on whether the goal is to provide authentication and non-repudiation. Authentication verifies the sender or receiver, or both, is who she claims to be. And non-repudiation ensures that the sender and receiver can't deny sending or receiving the message. If user A encrypts a message with her private key and sends the message to user B can decrypt the message with user A's public key. If confidentiality is a major concern for user A, she encrypts the message with a recipient's public key. That way, only the recipient can decrypt the message with his private key. RSA was developed in 1977 and was the first algorithm used for both encryption and digital signing and is still widely used today. RSA uses one-way function, a mathematical formula that's easy to compute in one direction, but difficult or nearly impossible in the opposite direction to generate a key. Diffie-Hellman doesn't provide encryption, but is used to establish a secret key shared between two parties. Although it's often thought of as a key exchange, each party actually generates a shared key based on mathematical key agreement relationships. If a key is intercepted during transmission, the network is vulnerable to attack, so key management is an important component of securing data. Elliptic curve cryptography, ECC, developed in 1985. It's used for encryption as well as digital signatures and key exchange. ECC is based on complex algebra and calculations on curves. It's an efficient algorithm requiring few resources, memory, disk space, bandwidth, etc. So it's a good candidate for wireless devices and cell phones. LGAML is an asymmetric algorithm used to generate keys, digital signatures, and encrypt data. The algorithm uses discrete logarithms that are complex to solve. Solving a discrete logarithm can take many years and require CPU-intensive operations. Asymmetric algorithms have a useful feature that enables a public key to decrypt a message encrypted with a private key, or vice versa. A public key can only decrypt a message that was encrypted with the corresponding private key. This figure shows an unencrypted message signed with a digital signature. The hash calculated from the message content is encrypted with a private key to ensure authentication and non-repudiation. In 1991, the NIST established a digital signature standard, DSS, to ensure that digital signatures could be verified. The federal government specified using RSA and DSA for all digital signatures and using a hashing algorithm to ensure the message integrity. The NIST also requires using secure hash algorithm, which is a digital signature that can be created by using only a user's private key, and the user's signature can be verified by anyone using this user's public key. Pretty Good Privacy, the PGP, was developed by Phil Zimmermann as a free email encryption program that allowed typical users to encrypt emails. Zimmermann was almost arrested for this unbreakable encryption because it was considered a weapon and compared with selling arms to the enemy. The internet standard for PGP messages is now known as OpenPGP. OpenPGP uses certificates similar to those in PKI, but is a centralized certification authority, CA, isn't used. Verification of a CA isn't as efficient as in PKI. OpenPGP uses an AES, IDEA, RSA, DSA, and SHA algorithms for encrypting, authenticating, verifying message integrity, and managing keys. Secure Multipurpose Internet Mail Extension, SMIME, is another public key encryption standard for encrypting and digitally signing email. It can also encrypt emails containing attachments and use PKI certificates for authentication. One reason that SMIME is widely used for email encryption is that it's built into Microsoft Outlook. As a security tester, often you communicate with clients by email. However, sending test results that reveal vulnerabilities of your client's network via unencrypted email, which is subject to interception, can result in a serious vulnerability. You want to make it a policy to exchange any test results or other sensitive documents in encrypted form. Organizations might also need to encrypt data at rest. This means any data that's not moving through a network or being used by the operating system. The term usually refers to data stored on workstations, servers, smartphones, thumb drives, backup, media, and laptop computers. A hashing algorithm is a function that takes a variable length string or message and produces a fixed length hash value called a message digest, used to verify the integrity of the data or message. Two different messages producing the same hash results in a collision. Therefore, a good hashing algorithm is one that is resistant to collisions. These are the different hashing algorithms. MD2 algorithm was optimized for 8-bit machines. MD4, using a PC, collisions in this version cannot be found in less than 1 minute. Microsoft Windows still uses this to store password hashes. MD5. In 94, it was estimated that creating a computer that could find collisions with brute force would cost $10 million. However, collision for an MD5 hash could now be found with just a few machines within a few hours. SHA-1, which is also known as SHA-160, has been considered broken since 2005, but is now approaching the date when collision attacks will begin to become available. It uses 160-bit digest and is found in many applications in the government and private sectors. SHA-2 is a collective designation for the longer digest versions of SHA algorithms. SHA-224, 256, 384, and 512. SHA-2 versions use essentially the same algorithm as 160, but the longer digests make collisions harder to find. SHA-3 KEKIC was selected as a SHA-3 standard by NIST in 2015. SHA-3 can take an input of any size and create output of any size. It is not intended to immediately replace 2. It varies greatly in design from its SHA predecessors.